Translating statements from English into first-order logic also often makes us be more precise about what we're saying. I'd like to illustrate this from these slides using the Looney pyramids that show up here. So we have different clusters of pyramids. We have 7 in the picture, or you could think of it as 8 if we think of having the empty cluster here as well. We have the cluster of all 3 different sizes and all 5 different colors. We can define notation for the colors and for the sizes. And then we can say each pyramid X in the set of pyramids in a cluster has a color that's from C and a size that's from S. We have some basic axioms about these colors and sizes. Every pyramid has one of the 5 colors, so for all X and P there exists a color, so that X color is that. But actually each one has exactly one of the 5 colors. So for all X and P there is a C1 where it has that color, and if you think you found a C2, well, then you've actually found C1 again. This is a standard idiom. We use it again for the sizes. Each has exactly one of the 3 sizes. For every pyramid, there exists a size 1, so that for every size 2, you have a pyramid having size 1. And if it also has size 2, then you just rediscovered size 1 again. You can't find 2 different sizes for the same pyramid. So I'm going to translate 10 statements from English into notation using quantifiers, starting with there is a pyramid of every color, and ending with for every color a pyramid of some size is missing. And we can look at these 8 configurations and see which ones satisfy these statements. The slides have more detail than this video, but let's try it with real pyramids down on the board here. There is a pyramid of every color. Sounds like we should say there exists a pyramid X in P for all C in colors. X of color equals C. But this is not actually going to happen. There says that if you choose the pyramid first and then ask for any color, then that pyramid has that color, but no pyramid has more than one color. So the problem is we have the quantifiers in the wrong order. We need the for all to come first. For every color C, there exists a pyramid X, with X color being C, and this is true for these 4 instances, and false for these 4 instances, including the empty instance, the instance with no pyramids. There are red pyramids of all sizes. Let's start on the inside. There's a pyramid, and the pyramid X has color red, and it has some specified size. Now we just need to add the quantifiers, and so there exists a pyramid, but we need for all size first, just like we had before. We're going to choose a size, and then we have to say there is a pyramid that is red and has that size. There are these 2 configurations that have the red pyramids of all the different sizes. There is no pyramid of any color for some size. The of any color is redundant, but let's write it down anyways. There exists a size, so that there does not exist a pyramid and X and a color C with X color equals C and X size equal S. We can use De Morgan's law to get rid of the negation, flipping the there exists quantifier to for all, moving it inside, flipping the and to an or, and negating both of the sides. Now we know that every pyramid does have one of the 5 colors, so there will be a color for which X color is equal to C, and this first part is false. And so for the for all statement to be true, we need that second part, the size has to not be equal to S, for the for all statement to be true. And so this really doesn't depend on color at all. And there are 3 configurations that are missing a pyramid of some size. 4. Every size is present, but some color is missing. This is false when we have all sizes and colors. It's false in most situations. There's only 2 situations in which it is true. After doing the previous ones, this should not be too difficult. Every size is present. That is, for all sizes, there exists a pyramid of that size. And it's not true that all of the colors are present, that for all colors there exists a pyramid that has that color. Now we can push in the negation again, changing the for all to there exist and the there exist to for all, and negating the equals. So for all sizes there is a pyramid with that size, and there exists a color, where for all pyramids the pyramid does not have that color. The remaining ones come in pairs, so we're well over halfway through, but this is a good time to pause and stretch if you need a break. The next 2 use almost the same words but have slightly different meaning. 5 is there's a pyramid for every color and size, which is true only for this one configuration. So we would say for all colors, for all sizes, there exists a pyramid that has that color and has that size. 6 is there is a pyramid of every color and of every size. For 6, we might think of it as there exists a color, for all colors there exists a pyramid of that color. And separately, for all sizes, there exists a pyramid of that size. I'm reusing x here, but because of the parentheses, it's a different variable. They're not the same. 6 has additional configurations for which it is true. These 2 have all of the colors and all of the sizes. All of the other configurations are false. 7 and 8 are opposites. For no size is there a pyramid of each color, or for some size there is a pyramid of each color. I'll just do 8. There exists a size, so that for all colors there exists a pyramid that has that color and has that size. There are 2 configurations for which this is true. These are the configurations where there is some size, so that for every color there is a pyramid of that size and color. The last 2 are also opposites. For some color there is a pyramid of each size, or for every color a pyramid of some size is missing. And this is essentially the same as the previous one, with the color and size swapping roles. There exists a color for all sizes. There exists a pyramid where the pyramid has that color and size. So this will be true when we have all colors and sizes. It will be true when we have all sizes of red pyramids. And it's false. It's also true where we have the black pyramids of all sizes, and it's false everywhere else.